Hello, welcome to Attacking and Defending Blockchain Nodes, where we're going to learn about a variety of risks and mitigations that we can implement to defend a very core component of the blockchain systems. We'll try to do a live discussion during the talk while we ask a question, so feel free to join DEF CON's Discord on BCV General Text channel, and I'll try to ask questions and respond live. In case we haven't met, my name is Peter Kacherginsky. I'm a blockchain security engineer at Coinbase, where I spend most of my time breaking a variety of different blockchain systems and smart contracts. I'm also a writer for the Blockchain Threat Intelligence newsletter, where I try to cover all the latest news, events, hacks, scams in the blockchain security ecosystem. Last year, you may have also participated in the Capture the Coin competition, which I helped organize. My background before deep diving into the cryptocurrency world was as a malware reverse engineer at FireEye, where I looked at a whole lot of APT malware, and a penetration tester for the Federal Reserve System, where I was breaking Finance 1.0. So just some give you an idea of what we're going to talk about. I'm not going to drop any old days today. What my goal here is to educate, to share knowledge, to also learn from you, with the goal of just discussing like how can we secure node infrastructure. So we'll start with a simple exercise on how do we know what is the state of truth that tells us how many coins we actually have. We'll go through a variety of examples of how nodes break, and we'll discuss a few of the ways that they could break in the future. Finally, I'll introduce a solid node security threat model for generic nodes, which you can apply later on for a specific node implementation. And most importantly, discuss a top 10 list of security defenses that you can implement today, whether you're a standalone operator or you're working for an exchange, and share lessons learned from trying to secure nodes of my own. So with that, let's talk about how many coins you have. So what is, if you wanted to, at any given moment, tell me how many coins of any given asset that you have, how do you go about that? So, well, you'll probably have a piece of software on your computer, on your phone, or a hardware wallet maybe, which has some specific logic dedicated just for a specific asset. So if you have a Bitcoin wallet or Ethereum or Monero or some other coin, sorry if I didn't list here, this particular wallet communicates with a wider network somewhere to the cloud and asks a question, hey, how much coins do I have? What do I actually own? In case of Bitcoins, you try to enumerate how many outputs that you have unspent. In terms, Ethereum is different in the sense that it's a count-based system, so you have to look up how much of the asset that I actually have on the network. The thing is, it gets a little bit more complicated. So if we start getting a little bit more granular, we're going to see that, in fact, we don't communicate with just some unknown entity, abstract entity. We actually communicate to specific nodes for that specific coin. So Bitcoin wallets communicate to Bitcoin nodes, Ethereum to Ethereum, Monero to Monero, and so on. This introduces some complications because we realize that there are a lot of third-party components involved. So if we just want to manage our assets, we have to communicate to a whole bunch of software which is maintained by third parties. So just to give you like a few more very simplistic threat model here, let's talk about components of a Friends coin, just the imaginary coin from the Mario Friends land. So you have your wallet communicating to a node, communicating to the overall gossip network of some sort, trying to propagate blocks. You also have your developers who are contributing to the GitHub repository, so you have to rely on maintaining the repository, compiling the node maybe, or downloading binaries there, and so on. And this all works really well, and until we start thinking that, well, how can we be sure that all the software libraries, all the standalone software infrastructure does not act maliciously, does not drop, modify, or craft transactions to steal your funds? So let's see how this could happen. So we have this Mr. Robot character trying to attack a variety of different points of this threat model. So, we'll start left to right. So we can see that we can attack the network connection between your node and the cloud. So if someone could start dropping blocks, try to eclipse attack your node. So to isolate it, to make sure it's not communicating to the rest of the network properly. The same character can also attack your node directly if there's some unknown weaknesses that they can exploit to do some kind of code execution or crash it. They can prevent you from accessing the network. At last, we also have to think about developers. The bad actors out there, they can go after developers, like the Toad over there. They can make them commit bad code. And I'll cover a few real world example where this does happen. So the idea is that it's an invitation to start thinking about the node security as a holistic ecosystem. So there are a variety of different components which are involved. So the examples that I just mentioned, they're not theoretical, they're practical, they're based on real world incidents. So for example, in May 2014, someone attacked the BGP network used to eclipse attack Doge and Bitcoin miner pools. So this was, in case you're not familiar with BGP hijacks, it's a way to effectively isolate whole large swaths of network blocks in order to make them route traffic to unexpected directions. This is something that happened a decade ago, I believe, with YouTube, where all the traffic was redirected to Pakistan, I believe, and it keeps happening again and again. This is a threat that we have not observed within cryptocurrency world for a while, but it's something that we have to be aware of and build threat models around. On the EOS side, after the release of the Node software, they published a bug bounty, and oh boy, did they receive a lot of good finds there, because one, there was immediately a code execution flaw that was discovered, and they, for a while at least, they kept on getting one after another of high value bounties submitted to them, which included denial of service, code execution, and similar. Finally, in 2019, Monero website was compromised. The binaries for the wallet were backdoored to steal clients' funds. So this is an example of how we have to look out for the developer. Where are you getting that software? How trustworthy is that resource? What can you do to verify it? So this was just over the few years, but I just want to instill in you, like, this is an ongoing problem. These are all the different things happening this year. So in March, we had on a testnet, but we still had a flaw discovered in the way Solana was processing transactions, where it was not doing sufficient validation. So it resulted in 500 million Solana getting stolen. Filecoin, again, had a nasty inflation bug, fortunately discovered on testnet, exploited also on testnet, but it resulted in 9 billion Filecoins minted when only 2 billion could have existed in the first place. Inflation bugs are particularly nasty because these are the attacks not against individual users, but against the entire coin ecosystem. Tendermint is a library behind a variety of projects. It's a consensus mechanism used in projects like Cosmos, Oasis, and others. A denial of service vulnerability was discovered there when parsing specially crafted invalid blocks, which basically crashed the nodes. So if this was successfully executed in the wild, Cosmos was luckily not vulnerable to this because they didn't upgrade just to that particular vulnerable version. But if that was the case and the vulnerability was maliciously discovered, then it would result in a network halt. The last example, and probably the most critical and interesting one, both from the impact and the way that it was handled, is Ravencoin. Ravencoin had an inflation bug discovered just last month in July. The inflation bug vulnerabilities basically allow someone to print money out of thin air, which is extremely dangerous because it allows an attacker to profit and sell value to exchanges, and it basically impacts every single user of the coin. What's interesting about this particular vulnerability was that it was actually maliciously introduced. It was introduced back in January through by an account which was seemingly making like adjustments to the way the comments were made on the debugging views were made. So, and the core developers unfortunately missed that until the point that someone reported them, a third party, which was building a blockchain explorer for Ravencoin, reports like, there's something weird going on in your network. And we're observing someone minting a whole bunch of RVN and also, by the way, selling them on exchanges and profiting from it. So the Ravencoin team was able to issue an emergency patch, worked with the miners, but it's still 300 million RVNs were minted and exchanged for some other coins. Something that we have to learn from. So before we go into the section on how to secure the nodes, how to look out for those vulnerabilities, let's first think about all the different ways that we can break the nodes. So just to define the scope right away, we're not going to talk about the features of a node, which are documented, and designs of the node. So if something implements proof of work, then we'll say we're not going to deep dive into 51% attacks, reorgs, other protocol design issues. We'll accept them as is. What we're more concerned about is if the node promises to do something correctly and it fails to do that, that's what we need to pay attention to. Key management is also outside of this. So if you're, you should probably running nodes on a variety of tiers. So if you just want something which replicates the state of the network, you should probably keep your keys on a separate system. Incorrect usage. So I assume that if you're running a specific node, that you read the documentation, you read everything that is known about it, so you don't necessarily make mistakes. Like a good example of that is Ripple's TF partial payment flag, where if you do not implement that particular flag correctly, then whenever someone sends you some payment with that flag set, it may appear that you actually received those funds, but in reality, it's an IOU essentially, that I will send you those things eventually, but not right now. So a lot of exchanges were exploited as a result of that. Finally, we're not going to focus on the layer 2 vulnerabilities such as smart contracts, DeFi, and so on. So what's in scope? What's in scope are the implementation flaws. So protocol, software flaws, attack resilience. Can the node stand up to sustained attacks? Infrastructure. So we're not looking at nodes as just this one thing and we're protecting just the node itself and don't care about anything that it's built on top. We're worrying about underlying OS. We're worrying about the network stack and anything that goes around it. Finally, management. Human factor is always was, always will be the weakest link in the security chain. So we will discuss access management. We'll talk about configuration, source control, and all other ops type of things. So with that, just before we dive into the exercise, just wanted to establish some terminology so we're all on the same page. The threat model, and this is taken from OWASP's excellent threat modeling cheat sheet if you want to review it and build your own threat models. Threat model itself is a process to identify potential threats. So we want to enumerate all the different ways that things can go wrong. We can assess those threats. What is the risk coming from them? Are they basically going to result in me losing money, or is it just a denial of service or some other maybe less critical impact? And also later on, we'll use that to prioritize mitigations. Why would we spend hours or weeks trying to address a risk which is not really that impactful? An important thing that we're going to do next, we'll define the attack surface. An attack surface, think of it as all the different ways that someone can attack your node or node infrastructure, and the threat agents, which are the entities which have enough skill, opportunity, and interest to attack your nodes. So let's begin with just a really basic system. It's not interacting with any other nodes. It's not managed by anything, just like a really basic core software. So we have the node itself, which all it does is it's processing the packets. It's processing the transactions, blocks, does verification. It stores the blocks in some kind of storage system. It parses configuration files, so it knows how to properly look at those things. And it may also include a VM interpreter process where it can interpret smart contracts or anything like full-blown Turing-complete Ethereum-style smart contracts or something a little bit more locked down like Bitcoin script. Now, let's add some more components to that. In order for Node to be useful, it needs to have some kind of management interface. And most nodes implement some kind of a RPC network client. So we have to think about the threats coming from that. Who can access this thing? What is it that you can do? And of course, node administrators themselves who are managing the machine, they can shut them down, they can bring it back online, they can reconfigure them and maybe introduce some flaws that I will cover in a moment. And also, these are just humans. Can they be attacked on their own with malware or maybe any other social engineering? Finally, nodes need to communicate to other nodes to figure out what is the state of the network. And this is where a whole bunch of different things are coming into play, like network infrastructure, other nodes that we need to talk to, and miners. So network infrastructure includes basically underlying layers of communication for the nodes. So think of BGP and DNS client, DNS services, and just basic routing like TCP connections, UDP. All of that is in scope and needs to be secured as well. Finally, nodes are just not appearing on your machines out of nowhere. They must come from somewhere. Unless you are the developer, you probably are relying on third-party repositories, which also in turn rely on third-party dependencies. So this is something that we need to be aware of, because as I mentioned with Ravencoin, someone was able to backdoor the asset through a very sneaky code change, and something that we'll also need to consider within our threat model. So with that in mind, join the BCV General Text on the DEF CON Discord channel and start. Well, I'll ask you questions to just brainstorm together on how we can break nodes. So the first thing we're going to attack is the core. This is the node software itself. This is what processes the blocks, the transactions. It needs to verify them correctly. If you are this, sneaky Mr. Robot character and you wanted to attack this, how would you do it? So I'll look in the channel for your responses. So I have one comment of software supply chain attack. So this is something that we're going to cover in the software repository attack, but I'm talking about the core itself. That's the piece of software that does the actual blockchain logic. BGP attacks to create an eclipse. So again, this is something that we have to worry about on the network connectivity side. Let's see. Yeah, so a denial of service against the node to crash with the bad blocks, malformed block headers. So that's exactly that. So we can craft a packet, think of a tendermint flaw, which basically crashes a node or maybe executes some kind of really nasty code execution attack. So just to give you some background, this is how I created the model. So there's a title, protocol vulnerabilities, severity. So if you can crash or do code execution on a node, the severity is high. Probability, I would say medium, is just harder to find, harder to exploit. It requires dedicated time to discover those things. But the impact is that anything that is not properly parsing blocks, transactions, what is the correct fork, messing with the governance and so on, inflation vulnerabilities, this is all in scope for this, and it will have a severe impact on the node. However, I want you to consider it's less sexy of an attack. So we're not trying to find some kind of ODE within blocks and transactions. And consider that nodes actually run all sorts of third-party software. So for example, parity nodes, they run, or Open Ethereum now, they run web UIs to manage the thing. A bunch of node software relies on third-party database libraries and standalone databases to store blocks. So all of that are fair game to attack as well. So if you are Mr. Robot and you wanted to attack your node infrastructure, I'm not going to spend time trying to find old days for the way that you parse packets. It's a lot easier for me to find out like what is the weakest link, what is the common off-the-shelf software that you're running, such as if you're running Nginx and for some reason it's a vulnerable version, I'll try to attack that as well. I'll try to attack that instead because it probably has more eyes on it and more vulnerabilities discovered so far. So consider those as your first line of things to lock down. And the probability is definitely higher than finding a very directed attack to, like in the way you parse blocks. So let's continue in the same style. So software repository attacks. So someone in the channel already mentioned that, the supply chain attack. So whether you're attacking the software repository itself, so you can, like a Ravencoin example or Monero example, if you can compromise the software repository itself, then you can introduce arbitrary changes, which are maybe different degrees of how hidden they are, depending how many eyes are looking at the repository. And again, this can result in funds theft or money printing type of vulnerabilities. However, what I want to invite you to also consider is not just the main software repository, but also software dependencies. So an example, not exactly a node vulnerability, but I believe it was Trinity Wallet, which had it was backdoored on the source code level. But the way that it was backdoored was not through the main repository, but through one of the dependencies. So someone figured out what is the weakest link in the supply chain to that particular piece of software, they backdoored that, and then they were able to introduce code that was stealing keys. So again, probability is high on that as well, and severity is also extremely high. I mentioned this before, human factor is always the weakest one. So node administrator, how can we attack that? Yep, phishing, send phishing email with some kind of malware. The impact is very high. They can reconfigure the node. They can introduce a set of nodes which they essentially creates an eclipse attack where you only communicate to something that is controlled by the attacker. Certain blockchains, they have a switch you can flip, which basically allows it to accept all blocks and transactions without doing any verifications, like a debugging mode almost. There are a variety of things that administrator can do, and the variety of ways that administrator can get attacked through phishing, malware, social engineering, you name it. The last, you get the gist of how we're going through different components. The last one I want to cover is the network attack. So correct. So BGP attacks to create an eclipse. So exploiting the network infrastructure. A lot of nodes, the way that they're built is that they need to first boot up. When they first come online, they need to communicate to something hard-coded to figure out what is the network truth, like what are the basic trusted infrastructure that I can use to start getting an idea what is the current block state. Well, a lot of them use protocols like DNS in order to find out like what is the first set of nodes that I need to connect to. And if your underlying DNS infrastructure is compromised, they can again try to do some kind of eclipse against you. Same with denial of service. If your nodes can never communicate over those protocols, then they will never be able to connect to the network in the first place. BGP routing attacks, those are extremely damaging and something that needs to be considered. I'm putting the severity as high on these, but probability lower, just because it's a lot harder to do a targeted attack to figure out what is the exact node that is owned by your company or by you individual. So it would most likely be an attack against the entire node network, but it's still probable. So we can keep going through all of these individual components and try to go through like what are the main threats. Luckily, I went through this exercise over the last few months, and I built a node threat model which applies to generic nodes out there. So if you take a Bitcoin node versus, let's say, Ethereum node, they will have all of these core issues, all of these core threats, plus whatever makes them unique from each other. So if you're, like I mentioned that, for example, Open Ethereum has an extra web server in there, so you'll need to slap in a web server into this model and consider like what are the threats there as well. Some more terminology so we can interpret the threat, the grid that I'm going to show you in a bit. So STRIDE is a common acronym used for threat modeling. It stands for simply just variety of bad things you can do, which is spoofing, tampering, repudiation, information disclosure, denial of service, elevation of privilege. It's just a guide to help you think better about like what is the impact there. It is also important to consider the likelihood. How likely is that the threat event is going to occur? How likely is that the threat actor not only has an opportunity, but also the expertise to exploit something, the weakness? This will become useful later on as we talk about mitigations and how to prioritize them. So overall in the threat model, we already went through the 11 components I showed you in a few slides ago. The total number of threats that I identified were 14, and the total number of critical threats for a generic node is 5. So again, depending on how your ecosystem looks like, if you're running a larger set of nodes and you have Dockerized images and all that, your threat model will continue growing. This is just to get you started somewhere and provide you foundation. So this is just a small glimpse into what the threat model looks like. We have the threat name, so node software generic vulnerabilities, the STRIDE impact, so elevation of privilege, denial of service, severity, probability, description, most importantly, a variety of different mitigations that you can implement to address this threat. So a key thing that we need to do when considering mitigations and the risk is to consider the cost. The cost, probability, and severity. So the cost is how much time is it going to take you? How many resources you need to invest to address something? What is the severity and probability of this threat? So in order to prioritize a variety of threats, I came up with this 5-level, criticality grid, where most critical flaws are the ones that are both have high impact, but also high probability of happening. Severe threats are the ones that have high impact, but maybe a slightly lower probability of occurring. So think of your generic web server getting exploited, which is running on your node, versus some esoteric block parsing vulnerability that needs to be discovered to be exploited. And all the way to low, where these are the threats which we can address at one point, but only after we're done with the top 2 or top 3 at least. So for all these mitigations, in the model, I created about 41 mitigations that one could potentially implement. There could be probably more that we can think of, but I'll share the top 10 ones in a bit. Of those mitigations, they're addressing 22 critical threats. What's interesting is that half of those mitigations for critical threats are in fact very low cost. This is something that you can implement in a day and will significantly bolster the security stance of your nodes. So yeah, you can start building fuzzers. You can start looking through every line of code of your nodes to make them secure, and they will make them very secure. But you can also do a bunch of things which are very low cost that will not make your nodes completely secure, but they will also, by the order of magnitude, make them resilient to some of the attacks that I described. So this is just a different view that in the top bar of the critical vulnerabilities, the ones in light blue, you can see that half of them are basically low-cost solutions that you can implement. And then you have just, if you really want to push it through this, like it's 99.999% secure, you can continue on that trail, but that will be a little bit more costly. So with that, let's talk about into node security, top 10 defenses that you can implement. So the first one and the most critical one, I think, is secure handling of where's the node software coming from, the repositories, the binary distributions, and so on. One key thing that we do at Coinbase, and something that you could consider as well, is repository pinning. Repositories can get compromised, but if you make sure that you pin to a specific known good version that you will work with and you will stick to until you go through some kind of process that, okay, I'm going to switch to the latest release instead of just downloading whatever is the latest one every time you deploy a node. That's something you could consider and could partially mitigate the risk of backdoored repos. Another thing is verification of signatures. So if you're relying on either source code that you're downloading or binaries that you're downloading, make sure you verify all the signatures. That in the case of Monero, if the binaries were signed and the attackers did not have signed signatures correctly, then you would be able to detect that. In the case of source code, if you can at least verify, like, who is committing to the repository? Is it coming from, am I accessing a website and it's, the TLS is not breaking, no one is man in the middle of me trying to download the source code? Again, this is something that could make your nodes more secure. We continue on that train of thought. We can also make sure that we build all nodes from source code. I know this is a big ask, but this is something that you could consider. And the reason for this is, again, the Monero example, where only the binaries of Monero were backdoored. The source code remained intact. And the reason why both could have been compromised, but if you consider how binaries for nodes are built, so there's a software repository with a lot of eyes. And then there could be a flow where one single developer with malware on their machine downloads that source code, builds the library, uploads the binary back on the website. There are a variety of things that could break along the way. Same goes with the CI automation of some sort, which builds binaries automatically. There are a lot more components which could be attacked and compromised, which is why, in case, again, lesson learned from that one incident is that if you just stick to the source code, it may still be backdoored, but at least you have like one point of failure as opposed to a multitude of others, which are required when building binaries. Secure node configuration. So every single node that I looked at has a whole variety of different levers that you can pull to make them secure. Some things that you should generically you could consider is make sure that you can diversify the number of connections that your node can make and to which nodes it can connect to. So an example would be things like Stellar, I believe. They need to be manually configured to distribute which nodes that you connect to. So make sure that if you configure nodes like that, you select as wide of a node selection as possible. Others, they restrict the number of connections total. So you want to see like what is a reasonable number of connections you want to maintain throughout the network. This will help you with Eclipse attacks, making more resilient against forks, and so on. Another important key on configuring nodes securely is locking down your RPC interfaces. So I believe last year there was mass scanning of Ethereum nodes that were looking for open RPC interfaces to basically steal private keys. So lock down your RPC interface. There's no reason why those should be exposed to the rest of the world. So make sure you configure, whatever IP or interface that RPC is listening on, make sure it's configured to something local to your network or just localhost. Restrict node access. So not everyone needs constant access to your nodes. Not everyone needs to be able to modify arbitrary things within your node. So at Coinbase, what we do is we create a consensus mechanism with no configuration changes, no nodes. No one can bring up and down nodes just arbitrarily. It requires a consensus of people. The more critical your infrastructure is, the more people it requires a sign-off. So you can implement it through a variety of ways, through GitHub, through some kind of two-factor pings that you can send to people to approve any given action. Define and enforce administrator roles. Again, this is something to restrict to secure nodes in larger environments, but you can apply this to individual nodes as well. Make sure that there are some specific roles set up for the node that you can either configure nodes and deploy them or shut them down, but not everything at the same time. So you can get very granular there, but it depends. See how appropriate it is for your specific environment. Finally, restrict node access, as in the network traffic node access, both ingress and egress. So on one side, it makes sense that you restrict your RPC interfaces already, so make sure those are firewalled off, that you cannot access node from anywhere, and then externally, you also have some kind of restriction set up as well. On the other side, nodes could be an excellent points of entry for the attacker who found some kind of vulnerability into the rest of your network. So make sure that your nodes cannot communicate to the rest of your network as well, because they could be used as stepping stones. Monitor and log node activity. So this one is probably the most interesting one, and there are a lot of things that you can do there. Anytime your node loses internet connectivity, make sure you do some basic verification. Is there like something with BGP, or is my DNS going down? Am I under attack? Am I getting eclipsed? So make sure you investigate those. Am I in the right fork? Am I not seeing sufficient traffic? All of that applies. You can do node-specific verifications too, not just generic network monitoring, such as like periodically check, like, am I in the right fork? What is the block height? What is the current block hash? Do other nodes in my system or externally or on blockchain explorers, do they still see the same thing? So in case of the recent ETC incident, you would have been able to quickly diagnose, like, oh, okay, so there's something going on with nodes because there's some kind of forking happening. Finally, log all access, all network events. It may not be as essential during the normal operation of node, but when something goes wrong and you need to investigate and figure out what happened, who accessed it, what were the network events that led up to the attack, those logs will be highly instrumental for the investigation. Lockdown base OS. So definitely, you cannot build a secure node software if your underlying layer is insecure. If you want to go after the weakest link and your node is very well configured and firewalled off, but your underlying OS is some outdated version of Linux, which has like exposed ports and they're easily attacked, the attacker is just going to go after that and going to skip all of the other mitigations you built. So you could do things like Dockerize your nodes, run SC Linux or similar toolkits. So there are a variety of things you can do to lock down the OS, and there are guides for that, but something to consider as well. Harden nodes network connections. So going up the stack a little bit, not just protecting what connections can be made or what we're monitoring, make sure that if you configure DNS server for your node, make sure it's a secure one, uses DNSSEC. If you're using ISPs, make sure that whatever BGP connections that it uses are done in a secure fashion. If your nodes needs to communicate to some kind of HTTP resources, make sure you configure your CAs properly so you're not getting met in the middle. Denial service protection is critical. Again, it's potentially hard to determine that I want to attack just one particular node for one particular user or organization, but it's prudent to use something like Cloudflare to have a layer of denial service protection so you don't have to worry about that. Node-specific threats, node and protocol-specific threats. This is a catch-all. Basically, be mindful that all nodes are unique in their own different ways. So I mentioned before that Stellar, you have to manually configure what are the trusted nodes. You have to manually calculate, like, hey, like, what is my threshold for? It's a BFT network. What is my threshold that it can get attacked? So make sure that I'm not going to be vulnerable to that. Other protocols like EOS, they implement like debugging modes that you have to watch out for. So read the config file completely. Make sure you understand it complete. What are the implications of all the variety of settings, and have a good secure configuration specific for that node. Verify node functionality before deployment. So that's a much harder one, because sure, you pin the repository, you are pretty confident, okay, so it probably was not modified, but I'm not 100% sure that whatever I downloaded is working as it's supposed to. There are no backdoors there. How do you verify that it still works as intended? Well, ideally, you would run a set of tests like, hey, if I transmit this transaction, it shows up on the network. Or if I see a transaction coming from the network, my account gets properly credited. And that's a big ask to implement for every single node. So one project which aims to solve this problem is Coinbase Rosetta project, which creates a kind of a middleware for a variety of different nodes to be able to speak the same API. So instead of implementing a variety of different calls to transmit a transaction, get a current block, get the current block hash and transactions in it, Rosetta creates a kind of a middleware for a variety of different nodes that you can just use a single API call and it automatically translates to whatever is specific for that node. Now, what's interesting about the Rosetta project also includes a Rosetta validator, which exercises the node and makes sure that it passes a variety of very specific tests from transaction verification, blocks, and signing, and so on, to make sure that it works exactly as intended. Not every project supports Rosetta interface, but for the ones that do, you can implement it in a pipeline to make sure that the nodes that you deploy are acting as expected. And you notice that we're slowly ramping up the difficulty level. This is probably the hardest one. This requires you to examine the source code, examine the alerts that you're getting, and this is the basic static analysis basic security static analysis of node software. So you may not need to go through the actual source code, but you can observe a variety of different alerts reported by tools like Salus. So this is another Coinbase tool which we use internally, and it's an open source tool you can use as well to quickly run through variety of node source code packages, and it gives you a nice report of what are the high critical vulnerabilities within that. So you can examine them, just get a general sense. It's hard to say which ones are false positives without actually looking in the source code, but you can see like, hey, if I suddenly see 100 or so, or like this really sneaky report, maybe I should investigate more or report it or ask the original developers. In the Salus project, it supports a variety of different languages from Go to Ruby and so on. GoSec, like for if you're just running Ethereum or other Golang based nodes, so GoSec is excellent. In fact, Salus is running a variety of open source projects, and it just creates a wrapper for them. So GoSec is one of them. For all the other projects, you have something like SemGreph, so if you have C code to analyze and so on, so you can use that as well. So with that, just to summarize, what is our total view of all the different mitigations? Top 10 things that you can do to secure your nodes. So make sure you handle software repositories securely. Make sure that you pin them, that you understand that they can be compromised, and you need to just investigate a little bit more. Build all nodes from source code. So again, it's just reducing your attack vectors just a little bit more. You just build everything from source. There are a lot of eyes in source code. Who knows what happens with those binaries? Securely configure nodes. So make sure that you diversify what connections your nodes have. Make sure that they can't be just as easily eclipsed and people can access it and reconfigure them. Restrict node access. Monitor and log node activity, so you can get, again, very creative with those, what you can do to judge what is nodes help. Log down your base OS. Make sure that you're not building your castle on quicksand. Hardens nodes connections. Definitely consider node and protocol specific threats. All nodes are unique in a variety of different ways, so you need to consider those as well. Verify node functionality. So if your node supports Rosetta project, run Rosetta validator. It will exercise until give you like this good feeling that, okay, at least for a variety of tests, this still works as expected. And then if you have time and you have technical expertise, try to run basic static analysis tools just to periodically see, like, are there like major low-hanging fruit vulnerabilities that are getting introduced that I can catch, maybe report to original developers. So with that, thank you so much for your time. I may have not mentioned this. I'm the Blockchain Threat Intelligence newsletter. I list a lot of the node incidents, vulnerabilities that are getting discovered. So subscribe, see if you can catch the latest lessons learned from those vulnerabilities, and feel free to follow me on Twitter, or feel free to contact me offline if you have any more questions. Thank you.